I'd like to introduce both Daniel and Joe, who will be speaking on time trial racing toward practical remote timing attacks. Thank you.
Good afternoon. Thanks for cutting your lunch break short to make it back on to our talk on time. I will talk about time trial and the practicality of remote timing attacks. Just a few words on who we are. My name is Daniel Mayer. I'm a senior security consultant with Matasano Security. I've gotten my PhD previously in computer science with a focus on security and applied crypto. And I give the talk together with my colleague Joel Sandin, who also works at Matasano. We are the application security company with offices around the US, and we're part of the NCC group. Brief overview of what we will be talking about. We start out by giving you an introduction on timing side channels, what those are, how they come about, and then go into the challenges you face when you try to explode those remotely and things which you may need to take into consideration and which make it much harder in order to exploit these kind of things. And as a third item, we present our new tool called Time Trial, which is a feasibility analysis tool, so to speak. So it allows you to do timing measurements and assess timing vulnerabilities in your own applications. And based on that tool, we then did a bunch of experiments both in different network scenarios to see what one can exploit in those, and then putting that into perspective with common functions you see in your own software to see what you can exploit in those environments in which you cannot. So hopefully after this talk, you have a better feel on what are timing attacks and do you need to worry about them, or which kind you need to worry about, what can be exploited, and what is more like a theoretical attack. So let's start out by talking about side channels in general. Think about if you have a web application and your main interaction with that application is usually you send a request, you get a response, and that's your main communication with that application. And if everything there is secure and you don't get any information out of the system which you're not supposed to, there may still be a way around that and other paths which you can try, side channels, in which you can gain information on the system. Unfortunately, the path is not as smooth as the previous picture showed you. It's actually a pretty rocky road. There's a lot of different difficulties along the way in exploiting these things. And if you go astray in one direction, it may quickly go downhill and nothing works at all. So to give you an overview what side channels are out there, they have been studied quite extensively, actually. There's power consumption analysis, there is RF, or radio frequency emissions, there's recently sound emissions, and what we will be talking about, processing time. And what all these have in common is that we can measure them outside the actual application or the actual system you're testing. It's the side effect you're measuring of the system, but it's related to what the computation, related to the computation the system does at a given time. And if that computation involves any kind of secret data or sensitive data you would like to learn about, then you can infer from our measurement, from the side channel measurements, you can infer something about that secret which is happening in the application, basically. And if you compare this to the more traditional vulnerabilities which we're all familiar with, like in the web space, we have cross-site scripting, CSRF, we have SQL injection. Those things are getting really well understood. We know how to defend against them. Developers are getting better at not introducing them anymore, and frameworks are helping a lot to make it much harder for them to be introduced in your software. But if you look at side channels, they're less well understood. And people are introducing them very innocently using regular operators in your language. And it's very hard to test for them. And even if you find them, you don't really know, are these exploitable? Are these issues real? Or are they just theoretical issues which your pen tester reported to you, for example? So we will be talking about the timing side channel specifically. And what we do here is we measure response times from a system. And we try to reason about the computation that happened based on the response time. So if you send a certain message to a system, it may take longer to compute than if you send it a different message. And we can measure those timing differences, and we can try to infer things which happened in the system at the same time. For instance, if a sensitive credential is being used and involved in the computation, we may be able to infer that. Or if certain branching is happening in the application based on secret system state, which you'd want to keep private, we can deduce that potentially. But the main question here is, in principle, those things are exploitable remotely because we measure time over the internet by using the application. But can these really be exploited? And that's kind of the question we hope to shed some more light on in our talk. So let's dig a little bit deeper into side channels. This is a very simple example for a basic side channel in Ruby. What this application does, it takes a username and a password, and it takes the username first, and it verifies if the username exists. And if it does not exist, it will reject at this point and will say username or password is incorrect. Only if the username is correct, it will actually check the password and go in the next step And if the password is incorrect, it will reject it with the same error message. So from a system standpoint, from the outside, you don't see behavior whatsoever. So you can't tell if there was a valid username submitted or not. But an attacker may be able to still distinguish these two cases based on the response time. So how would you attack this? The very basic idea here is you start your clock, the attacker starts their internal clock, and then sends a request to the server, sends it a username and a password. The system will first verify if the user is valid, and then return in the first step there, where we have the time t0. I'll try to get this done. And in the other case, it will actually go ahead and verify the password, and if that one is incorrect, it will reject here. So if we're able to distinguish the invalid user who responds at this point and the valid one down here, then we're in game and we can actually learn something about the system, in this case, just the rather boring whether a username exists. But the point here is we have to be able to distinguish two different response times, and it's not about measuring the actual time which is executing on the system. So there's been a lot of prior work, so we're obviously not the first people looking at this. This started out in the crypto community, where people tried to look at implementations of cryptographic algorithms and tried to make those constant time that you cannot learn something about keys. And that went into remote attacks by Bromley and Bonnet for an OpenSSL implementation where they could recover keys remotely, actually. And then more recently, there have been really excellent empirical studies, starting with Crosby's study, which they analyzed how different networks behave, and that's actually something which we based our work heavily on. And then in 2010, there was a talk here at Black Hat by Nate Lawson on the feasibility of these attacks. Has anybody seen this talk 4 years ago? Okay. So with that, I'm going to hand it off to Joel, who will be talking about the challenges we face in remote timing attacks. It's going to be a little bit more theory to see with statistics and how we analyze things, so bear with us. It's going to get to practical results really quickly soon.
Thanks. Thanks, Daniel. So let's talk about remote timing attacks in practice, what makes these attacks difficult, and we're going to look at the best known techniques for performing them in a network environment. So we look at local timing attacks. We really have the luxury of measuring time precisely, measuring the execution time of the target precisely, and we minimize external influences. So we don't have to deal with major sources of randomness or error in our measurements when we're doing the analysis. When we're doing a remote timing attack against a target on the internet, we can't measure the execution time of the target directly. The only thing we can measure is the round trip time to the target. So that includes the propagation time, the time it takes for us to send our request, the execution time, and the time it takes for the server to respond to our sensor. So what we're looking for here is the signal, which is the execution time. But what we're actually getting in our measurements is signal plus this random distribution of propagation times on the network. In an ideal world, network propagation time would be constant, would be consistent, but in practice it really isn't. And the problem we face here is kind of getting the needle from the haystack and learning something about the execution time on the target. And it's important to understand, and Daniel mentioned this, that we're not trying to measure the execution time of the target. If we could do that, that would be great. The question we want to answer when we're performing a timing attack is, did the target take longer to process one request versus another? If we can answer that question, we can do a lot. So if we're sending, say, a password to a server and it takes a little bit longer to respond, maybe that tells us that additional bytes of the password that we sent in one message match the expected value. Or we may be able to infer that the server ran a database query as a result of one request versus another. So being able to judge whether a server took longer to process one request versus another is really useful. So let's look at what do these measurements look like in a real system. So here we have a graph of round-trip time measurements against a cloud service provider, a DigitalOcean instance. And the x-axis here is the round-trip time in nanoseconds, and the y-axis is the frequency, or how many times we saw that measurement. And a couple of things jump out at us right away. We have this long tail of longer response times that are relatively infrequent. Most of the measurements are really skewed towards shorter response times. And we have multiple peaks of the most frequently occurring values. And there's this smooth ramp up in the smaller response times, very smooth. And all the way on the left there we have our minimum response time. So fitting something like a Gaussian statistical distribution or another parametric distribution to this data that we see here, it's not really going to work. We can't leverage the statistical techniques that we get with those kinds of distributions. So we're really starting from scratch here, trying to come up with a technique that lets us perform this attack in practice. So we want to, like I said, pull the needle from the haystack, is find a value in these measurements that correlates well with the execution time on the target. And a good candidate is the measurement all the way on the left in the graph, which is the minimum response time. And we know that that measurement is the execution time plus the minimum added jitter that was introduced by the network. And you'd think that, you know, with enough measurements that the minimum response time or the minimum propagation time would be something that's fairly well behaved in networks and consistent over many samples, or consistent between sample sets, I should say, if they're big enough. And, you know, one theory would be that we take a neighborhood around that minimum response time from two sample sets, compare them, and if they look different enough, then maybe we can draw some conclusions about the execution time being different. In practice, the minimum response time doesn't correlate as well as other measurements with the processing time on the target. So the minimum response time, it's actually a percentile. And a percentile is just, it's the minimum value that's greater than X percent. So the X percentile is the minimum value that's greater than X percent of the samples that we saw. So the 0th percentile is the minimum response time. The 100th, 100% percentile is the maximum response time. And we also have these very low percentiles, which is the lower response times that we saw in the previous graph. So if we see here, this graph actually tells us a lot about how these percentiles track the server processing time. And it's important to note that, so we're talking about a plot of the percentile as a function of server processing time. So each point on this line is actually taken from many samples. These are pulled from sample sets for each server processing time. And what we see here is that these low percentiles actually have a much smoother relationship with the server processing time compared to the minimum response time. So that gives us kind of a clue as to what techniques will work in this context. And the best performing statistical technique from previous empirical studies is the box test, and it uses these percentiles. So here we see again this histogram plot of our response times. And if we take the 6th percentile, and this is actually a better illustration of what I mean when I say percentile. This is, you know, we're drawing a line here, and the samples to the left of it constitute 6% of the samples that we have graphed. Or if you want to look at it another way, this is, to the left of this is 6% of the area of this blue curve. So a box is actually defined by 2 percentiles. So now we add the 8th percentile. And if you look at that range on the x-axis, that range of sampled response times, that's our box. That defines an interval. It's induced by these percentiles. And the percentiles themselves, the percentiles that we choose to use for this test, it's going to depend on the target. They're going to be determined empirically by, you know, doing measurements and figuring out which box actually performs well for our target. But in general, these percentiles are drawn from the low percentiles in the sample set. So now if we add a second set of samples, a second distribution that we've sampled here, and we see this corresponds to 105 millisecond execution time on the target versus 100 milliseconds for the blue distribution, the sampled responses correspond to that execution time. And we draw this same box here. So we see for the longer execution time is 5 milliseconds longer. The box actually occurs to the left of our box for 100 milliseconds. So we're basically confirming that one distribution is a time-shifted copy of the other. That's really what the box test amounts to. And we'll talk more about the effectiveness of this statistical method. And I should just mention that this is what's actually built into the tool time trial. And now Daniel will talk more about the architecture and capabilities of the tool.
Thanks, Joe. All right, so we use this statistical test, and we put it into a tool which allows you to use it in a rather easy way. But first, why do we actually need a tool for these kind of timing attack things? Well, there's no real good way to analyze the impact or the the exploitability which anything has if you see a timing attack in your code. At the moment, you say, well, theoretically, this is a timing attack, and maybe you just go ahead and fix it anyways just to be safe, but you don't really know if this is exploitable or if it should be maybe lower on your priority list if you have other things which you might want to worry about. So we hope that having a tool available will allow you to make an educated decision of this is a high risk, a no risk, or like a low risk situation for you when you have it in your software product. So what time trial is it's a framework to allow you to do precise timing measurements and to analyze those using the most advanced statistical methods which have been tested in previous studies. And it also allows you then to generate like visual proof of concept. So you can get these plots which we've seen before, and you can illustrate, okay, these are clearly distinct or these are not distinct, and you have some sort of indication on whether you should worry about such a timing attack or if you should not. What time trial is not at the moment is like a full exploit framework where you just put in an endpoint and say, hey, there's a timing attack, and you just get suddenly access to the service. So that's not the goal of this. The goal is to analyze if you actually have an issue, and if you wanted to go ahead and then use that knowledge to build an actual attack, you can of course do that, and you can use our tests to guide you in this. So when we looked at this, the main goal was to get precise measurements, and the best way we thought about doing that is going really low level and using C++, because we have access to the most precise timers on most computers these days. But at the same time, we wanted to have a nice front end for it so that you actually can use it and that you don't have to run command line utilities only, but you actually have plots and graphs and things like that. So we put a Qt GUI on a Python application. And both of those are communicating via a Redis queue. And the idea here is that we can take the sensor, which we call the racer, an analogy to the time trial thing. We dump that racer anywhere we want. So we can put the racer in EC2 if you want to attack somebody in EC2 and be close to that target, or we can put it on our network, or you can run it anywhere you would like. But you can still have the GUI application and control everything from your desktop. So the idea is you start an experiment from the GUI, it pushes it in the queue, the sensor executes all the experiments, sends the data back, and then you have your GUI where you get the results, you can plot them, analyze them, and make your decisions about it. One thing we thought about when trying to decide how to do precise measurements was not just using regular C++, but what about if we were using dedicated hardware? Because we cut out our noise all the way. We go down to the hardware level, and we were thinking about using network interface, which has hardware timestamping, like IDS systems oftentimes use this, or we're using FPGA, which has a network interface to do in hardware timestamping. But in the end, we just decided that Linux is actually the most useful thing because we can customize it and we can run it anywhere. So we can go to Amazon EC2 and we can rent a cloud instance there, and we can install our software and run it there, but we cannot ship them a network interface and say, hey, can you please install this for us because we would like to attack some of your people there. So in the end, we just ended up using a MacBook Pro for most of our measurements. But we did some optimizations to this. So we first of all, the timing measurements we are doing is with a nanosecond timer using a monotonic clock, which is available on most Linuxes these days. But we also try to isolate our sensor process as much as possible from the operating system. So we isolated one CPU core that is not being used by any other process and not by the Linux kernel itself. And then we assigned our process to that particular core. So then it runs there with high priority and it's not getting preempted by anything else while the measurements are running. We also disabled frequency scaling just to be on the safe side that we don't get any artifacts because of that. So with that, let me give you a brief demo on what you can do with our tool at the moment. Going to switch this to mirror. Can you see this? Okay. So this is the interface we have right now. Under the settings tab, the only thing you can really do is define your sensors. There's one in here which I used for a previous experiment. Basically, you can just give it a name, and you can give it a host name, and you can give it location just for your personal reasons. So the only reason we have this is there's different queues in the Redis queue which we're using for communication. So you can have multiple sensors running at the same time, and you can say, okay, this task should run on this sensor, and this task should run on this sensor, and this is just a way of distinguishing those. Then here on the experiments tab, an experiment is basically one set of samples you would like to do to perform a certain measurement. And you can just start a new measurement here. You can just call this like a 2014 and switch to this new sample. And then we can define our trials. The trial is one experiment against the system. And at the moment, the main thing we're supporting is an HTTP trial, as we call this. So it can run against any HTTP or HTTPS target, and we feel that's like a pretty substantial set of examples already. So we call this test, and then you say how many iterations would you like to run. This is basically when the histogram is being generated, how often do we try to measure the response time. Let's say this is going to be 10,000, and we want to run this on our new sensor on CPU core 1, use real-time scheduling, and then we can put some URLs in here which I have prepared. So this is just the URL which you're trying to attack, and then if you're familiar with Burp or something like this, you can just get any request you have in Burp and put it in here, just in repeater, and this will be parsed by our tool and will be using a C++ library to actually execute the request. So once this is created, it shows up in this list, and then if I would have a proper internet connection here, I could just say start, and it would launch it wherever the sensor is located, and would execute. And when things are done, the results coming back, I have this prepared here, so you see that there's a start time and an end time. So these ones have been run correctly previously. And there's the two cases. I ran a trial against a system which was having a valid username and an invalid username. And in the case it was a valid username, it would do one additional SHA-256 hash afterwards. And then as you will see, if I plot this, so this is the correct username should take longer because it does the password hashing. So I can say this is the longer trial for my experiment. And this one is a shorter one. And then I can move over to my feasibility analysis, and I see that there is the plot for the two distributions. And you can probably already see that the blue one is further to the left than the other one. It gets a bit more clearer if I add some bins for this. So the distributions are clearly separated. And if I then use the box test up here, and I say I want to have boxes between 6 and 8%, and plot this, I'm going to get these two bars, and I also get like an immediate indication that these distributions are distinct and that there has been a measurable timing difference in that case. And this is really one execution of SHA-256 using OpenSSL. There's not an attack against SHA-256, obviously, but it's not a big computation happening, but you can distinguish this remotely over the network quite nicely. There's a few more other options for defining the plot and things like that. I'm not going to go into that for now. So that's the tool. And so let's see what kind of data we got with that and what we analyzed so far. As you can imagine, if you have different kind of network settings, if you have a LAN, your network quality is going to be much better than if you're doing an experiment over the internet where you have transatlantic connections and things like that. So we looked at different network scenarios, like the LAN, internet at large, let's say, in different cloud environments. And we were looking at which kind of different response times can we distinguish in those environments. So remember, we have to be able to tell whether we had response time T0 or T1. So that's what we need to tell. So in order to do that, we built on top of the technique which Crosby et al. Developed. You guys are seeing something, right? Yeah, okay. I forgot to switch back from the mirror mode. So the idea of this experiment is that we have our server, which is on the left side, the attacker, and that server is sending an integer value to the server, which is our mock-up service to demonstrate this. And the server will sleep for a certain amount of time. So in this case, it will sleep for 1,000 nanoseconds, which corresponds to like an artificially created 1,000 nanosecond processing time. And then we can do this experiment again, and we say, okay, now sleep for 2,000 nanoseconds, and we measure the time for that. And if you can distinguish those two over a given network, then we know that we can distinguish the timing difference of 1,000 nanoseconds over this particular network. So let's look at some plots for this. So we started off on a LAN, and we had 1 millisecond timing difference. So these things are worlds apart. So you don't need any fancy statistical methods to see anything here. And then if you decrease the timing difference to 100 microseconds, to 10 microseconds, to 5 microseconds, we see the distributions are moving closer together, but even 5 microseconds, you probably can still see with the naked eye that these things are separated. If you go to 1 microsecond, things are getting a bit more difficult. On the top, you had measurements with 1,000 repetitions. The distributions look really at the same place, basically. But then if you increase the iterations to 10,000 to 100,000 repetitions, they become start to separate again. And we can see that the blue curve is actually to the left than the red curve. And our box test confirms that. So we did this a bit further, and the limit we found for the LAN is that we can to about 100 nanosecond timing difference in a LAN environment. We can maybe get better, but the problem here is that our artificial sleeping functions may have been a bit inconsistent. So the problem may not be that the measurement is not precise enough, but that our artificial sleep we introduced also added some noise to this. So we think that something close to below 100 nanosecond in a LAN is something which is pretty reasonable to detect. If you were to happen to be on the same host as your target, it's not a very likely scenario, but maybe in like virtual hosting environments where you have like Linux containers and you're actually on the same host, you may have such a setting. Here you can get below that. So this is a 30 nanosecond plot, and you may actually get below that if you're lucky, basically. Unfortunately, if you look at the WAN and the wide area networks, things are not quite as nice. This was an experiment from broadband connection from my home place to DigitalOcean, just to see like a regular connection which people would have. And here things are much more broad, and we can only distinguish something up to like 1 microsecond timing difference. So that's the limit we found there. You may be able to get better if you have a better network connection or a better vantage point. But in principle, over the internet, it really depends on where you are located and where your target is located and how the network quality is between there. So that got us to thinking, well, if that's the case, why don't we move as close to the target as you possibly can? So we did measurements inside of EC2. We just got 2 EC2 instances, and we wanted to see how good is their network. If we want to attack somebody who's on EC2, could we get on the same availability zone or close to them and run experiments there? And it turns out the networks in EC2 are really nice. They must have really good hardware. And we have a 100 nanosecond timing difference, and we can still distinguish that inside of EC2 instances, between different EC2 instances. You have a lot of more peaks here, which is probably because of the virtualization solution they're using. But if you zoom a bit in, you can see that there is a clear difference between the blue and the red curve, and we can, if you run the box test on this, you can actually exploit this. So the bottom line of all of this is that if you're local on the host, you can go sub 100 nanosecond really well. And LAN and EC2 behave very, very similar to each other. So here you can go up to 100 nanosecond, potentially a bit better depending on how your environment is. On the WAN, it really depends on the particular connection you have to your target, but something between 1 microsecond and 100 nanosecond seems like reasonable, probably closer to the microsecond range. And all these things are pretty consistent with previous measurements, so there hasn't been much movement from when Nate Lawson did this or Crosby did these measurements. They got into the same range. So our networks don't seem to have much improved, or our tool is not that great, but I don't think that's the case. So, but what does this all mean for you guys? Now we know what the timing differences are, but if you have a timing attack inside of your free software, how do you know which timing difference you have? So we looked at some real-world application scenarios and things you often encounter, and we try to gauge how do those compare to these timing differences, which we just talked about. And I'm giving it to Joel for that.
Thank you. Thanks, Daniel. Yeah, so let's look at the problem from the other side and talk about how timing attacks actually look in practice for some vulnerabilities you may be aware of, and also maybe some system aspects that you haven't thought about before. So string comparison is it's a timing side channel that probably immediately comes to mind when you hear about these side channels. And most string comparison functions leak information. They're designed to be fast, and they actually terminate as soon as they find a difference between the strings that are being compared. So that leaks information about where in the string the difference was found. So in the context of a timing attack, we see here an attacker is sending a request to a target, and the target is comparing this string against a valid credential. And over on the right here, it's comparing 1 byte at a time. And when it reaches the 3rd byte, it responds and says that the credential is invalid. The attacker can then brute force, try multiple bytes in that 3rd position and measure the, and sample the distributions. And if the attacker finds the next correct byte, they'll actually see a difference in the response time distributions. That's how it works in theory. But in practice, there's a lot of roadblocks along the way. So these kind of vulnerabilities are really easy for developers to introduce. They're introduced whenever attacker-controlled data is being compared to some secret information. And you see them all over the place. If you're looking at code bases and developers are handling computing HMACs, for example, let's say you have a web API and the request includes an HMAC to authenticate it. The server actually computes the HMAC and then compares the HMAC that they got in the request with the one that they computed. If that's done using a regular comparison, equals or what have you, then you have a timing side channel. Web API keys is another common place where developers compare these things insecurely. So they have a web API key in memory that they expect for the client they're getting the request from, and they go ahead and compare it using a regular comparison. OAuth tokens, they can be implemented using HMAX, or they can be opaque values like web API keys, and the same issues come into play. Web micro frameworks that have these middlewares to do things like authentication. A lot of times you'll see when they're handling passwords, first of all, they're not storing the password insecurely, but they're also doing a naive comparison between the password they get and the password that they're expecting. So all these things, it's very common for developers to introduce these side channels. And at the end of the day, a side channel, it is a concern. It leaks information, but it's a separate question to ask when you say, okay, so can we exploit this remotely? And before we go to the next slide, so the two things we really want to know here that we want to understand is how much time is introduced by one additional byte comparison for common programming languages. That's really important because that's the bump that you're going to see when that comparison actually matches one additional byte. So that's a really important benchmark when we talk about feasibility of attacks against these string comparison functions. And the other assumption that a lot of people make, and it's often unstated, is that the comparison function is naive, that it will return when the first non-matching byte is found. And Nate Lawson pointed this out a long time ago, is modern operating systems, modern CPUs, they actually allow you to compare entire words at a time atomically. And it's up to the platform to actually take advantage of this, but more and more systems actually do take advantage of this. So one thing we looked at is Java. So we ran benchmarks for comparison in Java. Java's been a target of timing attacks. In the past, it's slower than C, Python, and Ruby, and so on. So it's interesting to look at Java and see what does the performance look like in 2014. So if we look at string comparison in Java, and here we have on the x-axis, we're comparing two strings and the first non-matching index, the first non-matching byte, that's the x-axis. And the y-axis is the execution time, the total execution time of the comparison. And we don't see a smooth increasing line here. We don't see a smooth, we don't see this smoothly tracking the index itself. What we actually see is this staircase graph, and the jumps are happening once you go past a word boundary. So what's happening here is Java, the Java virtual machine, this was tested with Java 8 on the Intel CPU. It's actually comparing an entire word at a time. And when it exits, it's exiting at the same amount, it's exiting at the same time, regardless of which actual byte matched. So it is leaking information. When we see those bumps on those word boundaries, that leaks information. That tells us that an additional word matched. Problem is that words are really big. We're not talking about bytes anymore. Here in this case, an attacker would have to guess the entire word correctly in order to get the feedback from the timing to be able to infer that their guess was actually correct. And that's just too big of a space too big of a search space to really perform this attack in practice. But we haven't even talked about micro benchmarks. We'll get to that. But we can look at performance on a lower end CPU. So this is a 1 gigahertz ARM 32-bit CPU, Cortex A8. And we ran the same benchmark. This is with Java 8 for ARM. And what we see here is it is using a naive string comparison function. It is exiting on the first non-matching byte, and it tracks really well with the index. So this is actually better for an attacker because they're going to learn exactly where in the string, potentially where in the string the first non-matching byte occurs. But we also have to talk about the difference that one additional byte comparison introduces for the platform that we're looking at. And so we want to perform micro benchmarks. And here we're not benchmarking the whole system. We're trying to isolate and measure one basic operation in the system. And we tried to look at byte comparison. So Nate Lawson and Taylor, they did these measurements in 2010 for a 64-bit CPU. And for C, Ruby, and Python, let's just look at those for now. The numbers are daunting. We're looking at sub-nanosecond. These measurements are in nanoseconds. We're looking at sub-nanosecond numbers here. So performing this attack over a network where we have 100 nanosecond resolution, or let's say we improve the tool and we get to 50 nanosecond resolution, we're still way off on actually being able to perform this attack against these comparisons. If we look at the i5, these are the benchmarks that we ran. First of all, the numbers are pretty strikingly lower, but I should also mention that these are no longer per byte values. Now we're talking about the microbenchmark for the word comparison. So these numbers, this looks like we're doing 2 word comparisons per clock cycle, which is not hard to imagine. The other side of it is when you're writing these microbenchmarks and you're trying to isolate this operation, the compiler, the CPU, and the operating system, they're doing everything they can to run this benchmark as quickly as possible. So I think for C, Ruby, and Python, the truth is somewhere in the middle. We were already looking at really difficult numbers in 2010, and they've just gotten worse. In Java, we see this is a friendlier number, perhaps. It's 7 nanoseconds. But again, this is for an entire word. So not only do you have to guess an entire word when you're performing this attack, you're only getting a bump of 7 nanoseconds. So I think we can pretty safely say that these attacks are just infeasible for modern hardware. If we look at the 1 gigahertz 32-bit CPU, the story is a little bit different. Python, Ruby, and C perform quite well, but Java is kind of putting us in the ballpark of possibly being able to perform this attack. So this is really more of a risk today for embedded systems, for lower power systems, and this particular attack isn't going to affect modern hardware, or it certainly is a lot harder to perform these attacks against modern hardware. So let's move on to some positive results, and I'll pass it to Daniel.
Right. So yeah, look at the more happy side of timing attacks and what actually can be done. So the somewhat different side of this are branching-based vulnerabilities, as we call them. So they're just, if your system takes a different code path depending on whether a certain decision has been made based on a secret value. So the simple example here was the username enumeration from earlier. If we can distinguish if a username was valid or not, we can learn something about the system. And what exactly the timing difference there is really depends on your application. So there is not a generic statement we can make about that. If you, let's say you have this username enumeration and either it returns immediately or it performs a logging operation to your file system, it does a SQL query, it maybe notifies Splunk that something happened. If all these things happen, you're going to have a huge timing difference between that. But if there's only a very small operation happening, if the username was valid, then we can maybe not distinguish this. So in order to make a decision about this, we just looked at some common scenarios here. The first one is we actually looked at the hash function, and I kind of showed you that in the live demo earlier today already. So we have the same example where either a hash function happened or did not happen. And here you see a SHA-256 hash function happening or not happening. It's pretty clear on the LAN. And even over the WAN connection to DigitalOcean I was using, I could distinguish whether the server was performing a SHA-256 hash or not. So this is not a complicated operation. If you think of anything which includes I/O on your system, you can almost 100% positive distinguish that remotely, because I/O is just taking so much longer than just a hash function, because these are highly optimized for speed. But something slightly more interesting maybe is, are you guys familiar with CBC padding oracles? Have you heard of those before? I cannot explain the full concept right now, but the idea is here, these came about several years ago, and they have been well studied, and there have been a lot of vulnerabilities. ASP.NET notably was really vulnerable to this. What it is if you have a server endpoint which you can send an encrypted piece of data, it will decrypt it for you. And if there is an error in the decryption process, we may learn something about the padding of the message. And the padding in this case is if you have AES as a block cipher, you have fixed size blocks which you need. And if your message is longer or shorter than a block, you would need to fill it with some padding. So what most algorithms do, for example, OpenSSL implementation, they perform a decryption of the data you give it, and they check if the padding was right or not after the decryption. And if it was not right, it will raise an exception. But if the padding was correct, it will assume this is correct data and will continue working with that. So traditionally, the problem was that the case for decryption was successful, which we have over here, would throw an error message out to the user, and the user could just see an error message and could say, okay, there was a padding error, and I can exploit that to actually exploit this padding oracle, which allows me to decrypt any data I want. So it's a really severe vulnerability. But even if you don't get an error message from the system which informs you that there was a padding error, you can still see a timing difference in these behaviors. If the system decrypts data and it's unsuccessful, it will give you an error message right away. But if it's successfully decrypting that data, it will try to process it in some form usually. Either it will do an XML parsing on that maybe, or it will try to do a database lookup, do something with it. And the idea is that we can distinguish that with a timing attack. But again, it depends on what this process data part is, because that could be something quick, something longer. So we took something which is really small. We just used a SQLite in-memory database with only one entry in it. And we made, if the decryption was successful, we looked the decrypted token up in the SQLite database. And if that token was in there, we send an OK message, otherwise we send a data parsing error message. So as you can see here, you can easily distinguish that on the LAN. This is just one SQLite query on like a really small table in an in-memory database. So it's definitely possible to exploit those things. So in order to show you that this is actually possible to run this, I have a small demo about this. And we try to make this Hollywood style. It's going to decrypt byte by byte, like you see it in the movies. So here we have, pre-recorded that. On the left side, we have the server, which is running a Ruby server. On the right side is our padding Oracle attack thing. And it's just running requests against the server, going through each byte, and for each byte trying all possible combinations and trying to find the byte which is actually inducing a longer timing response. And when it has a longer response, it knows the server tried to process that particular piece of data, and it knows that the value it found is the right one for the decryption. And then byte by byte, we can just go through this entire block of data, and we recover a word at a time. I mean, not a word, like a character at a time in this case. So this, in this case, I just made it a bit easier for myself and had a somewhat longer timing difference that I could run it that fast. But for each of these characters, usually an attacker would just make like maybe 100 requests, take the distribution of that, run the statistical analysis I just showed you before, and can then say, okay, this one took longer than all the other ones beforehand, and knows it found the right byte. So this should just show you that branching-based things are not only the boring user enumeration, which I showed you before, but there is actually real vulnerabilities which you can exploit through that. And that's the problem. So what is the takeaway of all of this? Well, the computing performance continues to improve. I guess we're not really surprised by that. But what we've seen before is that the timing differences for string comparisons get faster, that most CPUs are taking advantage of doing full word comparisons, and so everything is getting more efficient and much harder for an attacker to actually see one-byte differences. We might need to brute force a full 64 bits, which is infeasible today at least. But on the other hand, we see that these branching-based vulnerabilities are often feasible. So there's a good way of having these vulnerabilities in your applications, and it really depends on where they are to determine if there's any risk for you. And especially lower-end systems, like embedded systems, are at greater risk of this. We have seen, Joel has talked about Java and ARM as a quite feasible target. And we actually looked at an Arduino, which only runs with 16 megahertz. And there you can actually do string comparison timing attacks on the Arduino because it just takes so long to do one additional comparison. So that's actually something, it's just like 0.5 microseconds, I believe, for one string comparison. So what can you do? Well, the first thing, easy thing to say is, well, just make sure everything takes constant time, which involves sensitive data, right? But even the crypto community has tried to do that for a long time, and they needed multiple iterations for this in order to get it right, and it's really difficult to figure this out. So you have to look at your code and focus on the branching side channel things. If there is something like that, like the CPC padding Oracle, things like that are something to look for. You might still want to use constant time comparison functions. There clearly is a timing leak there. It's most likely not exploitable from remote, but people may be able to get better vantage points closer to your system. They may be able to tap wires directly. There is all kind of possibilities you can think of. So best practice would be just use a constant time comparison function for strings. They're in most frameworks these days, and we have examples in our white paper which can give you some guidance on what to use there. And then monitor your environment. Make sure if you see somebody doing like 100,000 requests, like what you would maybe need to do for such a timing attack, make sure you have something in place that notices that and that you can respond and maybe block out that client if it's misbehaving. So future plans for us are doing some more empirical studies. We're a bit interested in database queries and see if we can learn something about the database structure by observing response times, and maybe implement some more feasible attacks, things like the RSA padding Oracle, which is more a crypto-related thing, or anything else which may be actually feasible in practice. The other thing we noticed towards the end of our study basically was that since jitter changes over time, if you ever looked at network graphs, they change over time. It depends on use of people. The routing may change along the way. So what we did for our measurements so far was we always did all the short measurements first and then all the long measurements afterwards. But this may take several minutes, or for really long runs, it could take an hour or more. So the network topology, or not topology, but the distribution of the quality may change over time. So what we might want to do is interleave our measurements. So do first one short measurement, then one long measurement, then one short, one long, and have them, so that way both measurements see a much closer quality of the network during the experiment, and then we may be getting a much better resolution for our timing attacks. So that's something which we're going to do in the near future. So with that, the code for this is actually open source. It's up on GitHub. It should be public right now. We also have an updated updated white paper on our research page on our website. And yeah, I'm opening it up for any questions you have.
What's the most complicated rate number you guys find?
Rate limiting?
Yeah, because that's kind of what you guys are finding. That's back to 100,000 plus per day. That's a big start.
Yeah, that's a good point. So we didn't run it against, I mean, we obviously didn't attack other people. And so at the moment, so EC2 was apparently okay with us running these experiments between their hosts. We owned them both, right? So EC2 didn't do anything, even though they're known that they, if they see malicious traffic, they would do something about it. So we didn't see anything there. But it's definitely something worth exploring if one uses rate limiting, like common products which are being used for that, and to look into how that would affect these measurements. We actually haven't done that yet.
Would you be interested in testing out a very unique rate limiter? I will give you full permission.
Yeah, let's talk offline after this, definitely. Any other questions? Oh, sorry, didn't see you.
Have you considered using any sort of Bayesian or explanation theory to be able to separate very, very close distributions?
We have not. Do you know somebody did this before?
I haven't seen any research into using Bayesian, like machine learning stuff for doing the hypothesis test. There's probably better hypothesis tests out there, but we just went with the one that has performed the best in previous empirical studies.
Yeah, so Crosby analyzed various statistical techniques, so they did also the student t-tests and other ones which are in that direction, but they didn't go into the machine learning direction or anything, or filtering or things like that. But that may be something to explore. If you have any insights into that, maybe it would be nice to talk. I don't see any other hands. Right, go ahead.
Since that this mid-service depends on what are huge number of attacks that it
I'm not sure I heard it fully. You're saying that it relies on a large number of requests? Yeah, it does. So that's why I think why these kind of attacks are also easy to detect to some degree. I mean, if somebody is doing it aggressively, and like really hitting your server with all these requests, you should pretty easy to detect it. Of course, you could just spread it out and spend a long time. If you have if whatever you're attacking is not changing over time, you could spread it out over a year if you wanted to, and like make only one request every few seconds or something like that. But then you have the problem that your network topology changes or the quality changes over time, and then your distributions will be much harder to match up. So it's very challenging to do these attacks, and you need a large number of samples. Yeah. Yeah.
Have you done any experiments to see how well these things work on like, I presume all of your experiments are done on things where your process is only using things
Yeah.
what happens to other stuff going on?
Yeah, we haven't personally looked at it yet, but people have looked at that before, and they find that if you bump let's say that you put the server under load, like the target under load, and then you just put your requests on top of that, and I think they were in the low 10th% increase in jitter. So they noticed that it was maybe like 10 to 20% more jitter. Don't quote me on the exact numbers, but it's the Crosby study investigated that. So it's not like an order of magnitude different, but it adds definitely some more challenge. Okay, I think we're out of time, but yeah, maybe one more.
Have you found a difference between virtual machines and hardware? Is there a significant difference?
Yeah, so that was interesting to see. the LAN measurements you've seen, they were actually real hardware, and like bare metal running on bare metal. But the EC2 things were virtualized. So the main thing we saw is that the distributions were not like one peak and nicely distributed, but they had many more modes, many more maxima. So that would be worth exploring some more. But I think it suggests that there is like some preempting happening, and maybe another virtual machines executing for some amount of time, things like that. But the nice thing was, if you repeated the two measurements, even if they were minutes apart, the shape of the distributions was still the same. So it must be some intrinsic mechanism from the system. Maybe we can even use it for fingerprinting or things like that. So it was like an idea we had. Yeah. Thanks.